This video is about microphones, with special attention to Electret microphones. It corresponds to the first part of Chapter 26, primarily Section 26.1. Let's remember what the purpose of a microphone is. It's to convert sound, pressure waves in air, into electrical signals. And there are several different mechanisms for doing that. Let's take a look at a few of them. Perhaps the oldest one is a fairly simple one. It's the one that's used in dynamic microphones, and it basically consists of a coil of wire in a magnetic field. The magnetic field being provided by some sort of permanent magnet. When the coil moves, it's connected to a diaphragm so that the movement is caused by movement of the air. When the coil moves, it creates a voltage across the coil. So this produces a voltage output, and because this is a coil of wire, it's a fairly low impedance device, and that means you can get a fairly substantial current from a dynamic microphone. And dynamic microphones are still fairly common. They're used in two applications primarily. You will find them in recording studios where they're a traditional sort of microphone, and those are fairly expensive. You'll also find them in very cheap devices like baby monitors and intercoms, because a dynamic microphone is basically the same thing as a loudspeaker but run backwards. In a loudspeaker, we put current through this coil, and it reacts with the magnetic field to create motion of its diaphragm. When we're doing that, it's called a voice coil, and the diaphragm then is the cone of the loudspeaker. So it's basically the same thing. You can run a loudspeaker backwards. You can take a loudspeaker and use it as a microphone. It's not a very good microphone because the things that make a loudspeaker good, like having a large area for the cone, are not good for a microphone, and that you end up with a large mass to the whole voice coil movement and stuff. So generally you only see this in fairly cheap devices where you use the same device as both a loudspeaker and as a microphone. So baby monitors, push-to-talk intercoms like you have on some apartment buildings to talk from the front door to the apartment. Those sorts of things often use use the same device in both directions. We're not going to do that. There are other styles that we can use for microphones that are perhaps more interesting. One of them is a piezoelectric device. Piezoelectric devices respond to pressure by producing a very high voltage at very low current. And they don't get used much for audio work, but they do get used quite a bit for ultrasonics. Almost all the ultrasonic transducers I've seen are piezoelectric ones. And that's because you can get a very high frequency with the piezoelectric devices. They respond very quickly. The dynamic things, not so much, because the inductance there tends not to work really well at high frequencies. But piezoelectric ones like this ultrasonic transducer here that is intended for use in one of those rangefinders where you put out sound from a transmitter and listen to it with one of these receivers. Both the transmitter and the receiver there are piezoelectric. They're also resonant, so you hit it and it rings at a particular frequency. I think this one is set to something like 40 kilohertz. And they're very cheap. They're fairly efficient at the high frequencies, which the other devices we look at are not so good for. The piezoelectric ones, they're again voltage output, but they're very high impedance, so that you don't get much current, and they're fast. We won't be using them in this course because I I didn't find a piezoelectric microphone that was cheap and good for audio frequencies. And in fact, they're not the most common type. Neither are the dynamics. The most common types these days are capacitive microphones. And the capacitive microphones come in several different flavors, but the basic mechanism for all of them is that we have two plates of a capacitor. One of them is flexible and is the diaphragm of the microphone. The other plate of the capacitor is fixed. They're close together, and so what happens is when you move the diaphragm, the spacing of the capacitor changes. The area doesn't change, the dielectric between them doesn't change, but the spacing changes. So what we have there is a capacitance that is proportional to 1 over the distance. Okay, so we've got something that's a change in a physical property as a result of change in distance. That change in distance, incidentally, if we make this diaphragm to be like an ordinary linear spring, the distance that you have is proportional to the pressure. So this is proportional to 1 over the pressure. And perhaps I should say more precisely that the change in capacitance is proportional to 1 over the change in distance, which is also, or the capacitance is also proportional to 1 over the change in pressure. Because we're not looking here usually at DC measurements, but only at changes. There are several different types of capacitive microphones, and mostly they work by having some mechanism for changing this, for detecting this capacitance and changing some electrical property that's easier to measure than capacitance. One common way to do it is to put a charge on the capacitor. Now, if you've got a fixed charge on the capacitor, well, that charge is the capacitance times the voltage. If the capacitance changes, the voltage has to change inversely. Now, this is different from the way we normally think of it, where we normally think of capacitance as being fixed, so that as voltage changes, the charge changes. Here, the charge is roughly fixed, and as the capacitance changes, the voltage has to change. And so the voltage is going to be proportional to 1 over the capacitance, or in other words, it's going to be proportional to the pressure. And that's precisely what we want to have. And again, this should all be the derivative of the voltage with respect to time is proportional to the derivative of the pressure with respect to time. These are all measuring changes, not fixed things. Okay, so what types of capacitive microphones are there out there? There are ones that, in fact, just have this capacitor, and you have to put a pretty large charge on it with some external circuitry in order to get this behavior. There are also, for our purposes, two other types: Electret and MEMS. The Electret microphones, which are the type we're going to look at, manage to get this permanent charge by a very clever trick. And that is, they use something that's basically a permanent charged field in an insulator. And the way you get that is you take certain plastic or wax-like materials, melt them, and put a high electric field across the insulator, and then let the insulator cool down. So you melted it so that the molecules could rotate and move around. And then, keeping the electric field on there, you have oriented all the molecules to that electric field. Then you cool it so the molecules can't move anymore. You've now got that orientation of all those electric dipoles in the plastic or wax material permanently aligned. It's too cold for them to move. That permanent electric field basically is the same thing as having a charge on the capacitor. And so if that Electret material, which is insulating material, is part of the insulator of this capacitor, then it's contributing to the capacitance, and we get all the behavior we want out of this. The MEMS microphone is a little bit different. The MEMS microphone uses silicon wafer that is got the electrical circuitry on it that handles the conversion into whatever other properties you're using. And on there, it makes a very thin area of the silicon so that you end up with sort of a well where you've got a plate on top and a plate on the bottom with an air gap in between. And because this is very thin silicon, it's flexible and can flex with air pressure. And you've got the capacitor there built into the same piece of silicon as your electrical circuitry. So that's what the MEMS stands for, is microelectronic machine something or other. Forget what the S stands for. The MEMS devices are now the most common of the microphones because that's what gets used in cell phones and laptops. And the reason for that is that these things are tiny. We can get 1 millimeter to 2 millimeter microphones, including a lot of the electrical circuitry that goes with the microphone, in a tiny little can. One problem with it from our standpoint is that all these MEMS microphones are surface mount components. They are tiny and they are designed to be soldered down, usually all the way around some rim of the device, onto a printed circuit board. They do not work well with breadboards. Now, you could get a MEMS microphone and solder it onto some sort of breakout board and then plug the breakout board into the breadboard, but that starts getting fairly expensive. And if you do it yourself, soldering the MEMS microphone on is a real pain because you've got to be very, very careful not to get any solder into the tiny little hole that provides the air access to the microphone diaphragm. So the MEMS microphones are the most common type these days because they get used in cell phones and laptops. The Electret microphone is the type we'll have. So here is the sort of Electret microphone we've got. It has got a metal can around the outside. It's got 2 wires coming out at the bottom, and those 2 wires are conveniently 1/10 of an inch apart, so this plugs directly into a breadboard. So these are also quite cheap. They're in fact even cheaper than the MEMS microphones when you're getting them in small quantities. So this is probably the cheapest sort of microphone out there, and they do get used quite a bit. Most of the USB microphones and stuff like that use this sort of Electret microphone. Let's take a look a little bit at what goes on inside an Electret microphone. So I have found a website from Open Music Labs that has done a teardown of one of these Electret microphone capsules. So it looks a lot like the one we have, perhaps a slightly taller one than we have, but it's essentially the same inside. Okay, so here they've got a nice front view of it, looking just like the one we have. Back view, looking again just like the one we have. Here they've torn off the cover on the front so that you can see that there's a hole in that can, and the cover there, the dust cover is there just to keep stuff from falling into the hole. Okay, and here they have taken the can and cut around all the edge at the bottom, or pried it apart, something like that. And now you can see that there's several pieces here. We've got the dust cover, the can itself, the diaphragm, and then the amplifier module there as a big block of stuff that they haven't taken apart yet. Okay, so here is the Electret on the left, mounted on a metal ring so that the conductive layer is it's a very thin layer of metal or metallized mylar or something like that that's conductive. That's often quite fragile. It also needs to be supported on the edges, so there's a metal washer there to support the edges of it. And then there's a plastic spacer. That plastic spacer is to keep this thing from making contact with the other plate of the capacitor. So here's the other plate of the capacitor there. It's got some holes in it. These holes in it are to provide pressure release, because if you had the 2 plates of your capacitor, one of which is flexible, and you sealed the air inside there, then when the barometric pressure changed, you would be putting a lot of force on that diaphragm, either if the pressure dropped, pulling it out away from the microphone, or squishing it in against the other plate of the capacitor. So you want to have this one so that it's sort of resting in a natural position for recording the sound. And to do that, you have to match the pressure between the plates to the pressure outside. Now you want to do this with a fairly slow pressure change between the plates, because you're only trying to eliminate sort of the very large pressure changes due to barometric pressure and not the tiny fast fluctuations due to the sound you're trying to listen to. So just about all microphones have some sort of pressure relief mechanism like this that limits the low frequency response, because at very low frequencies the pressure release mechanism lets the pressure equalize on the two sides of the diaphragm and it doesn't move. And so these microphones like the one we have, they generally have a lower frequency limit of something like 10 hertz, which is plenty good enough for recording audio. But if you're trying to measure DC pressure changes, so you really do want to get barometric pressure information, then you need to use a DC pressure sensor, like the one we use in the pressure sensor lab. Those generally do not have any good high frequency response. So there's a sort of engineering trade-off. You can either get good high frequency response but not get down to DC, and for that we use microphones, or you can get down to DC but not get the high sensitivity that you need for making a microphone. Okay, let's see what else we've got. There's another device there that's just behind the plate that they've called here a transistor. And that is in fact a junction field effect transistor. We'll look at that a little bit more in a bit. And the gate of that transistor is pressed against the plate. And the other two wires of the transistor are the source and the drain of the transistor, and they're the two wires that come out the bottom of the microphone. And here they show you the transistor unsoldered from the bottom of the microphone, and the particular one that they've got, they actually managed to find out what type of transistor it was. I think the one they mentioned here is no longer being made, so probably we have something different in ours. The printed circuit board that's on the bottom that transistor was soldered to has got two central areas that are the lands for the soldering of the two wires. One of those has connections out to that outer ring there. So I can't really point with what I've got here. That outer ring is connected to the can of the microphone. So the entire can of the microphone is connected to one of the two leads on the bottom. So you have to be very careful about bare wires and stuff touching the can, because that can is connected to one of the leads. That lead is usually the source of the junction field effect transistor, which is the negative end electrically. We have to worry about polarity on these microphones because of the internal amplifier circuit that's provided. And we'll be looking at that more in the microphone lab, where we'll actually do some characterizing of the field effect transistor that's inside the microphone can. Okay, so here's a picture that sort of puts it all together. We've got the dust cover on the top, the aluminum housing that's the can around the whole thing, the metal washer that connects the can to the diaphragm, with the Electret material, very, very thin layer on the back side of that diaphragm. Then we have the plastic spacer to keep from short-circuiting the whole thing. Then we have the pickup plate, which is that plate with the holes in it that's the other plate of the capacitor from the diaphragm. Then we have the transistor with the gate pushed up against the pickup plate. We have a plastic housing there just to hold the pickup plate and the Electret materials and stuff, all that stuff, in place. And at the bottom, a printed circuit board to hold the transistor in place and to get a nice electrical connection between the source of the transistor and the can, which is again the connection that goes back up to the capacitive plate on the Electret. Okay, so let's take a look just briefly at what the circuit is that this thing is doing. I can draw it over here. We have got our variable capacitor, and one end of that is connected to the gate of a field effect transistor. The other end is connected to the source of the field effect transistor, and then we have coming out of the microphone both the source lead and the drain lead. We have no access to this gate lead. The capacitor, remember, was an extremely high impedance device. There was almost no current. Luckily, the junction field effect transistor takes almost no current. It just needs an electric field here that controls then how much current flows through the field effect transistor. And we will look at that in a subsequent video. But for now, it's enough to know that what we have in our two-terminal device, it's electrically polarized. We have to have we have to have a positive voltage and a negative voltage, positive on the drain, negative on the source, in order to get a current that we actually measure through here. And that's probably enough for now on the Electret microphone. We'll come back to the junction field effect transistor in a little while.